So we're going to start this section on rates of change in the natural and social sciences. This is on page 179, and we're given the equation for the first problem. F of t is equal, and we've seen problems like this before, t to the third minus 12 t squared plus 36t. So the questions go like this. Find the velocity at time t, which is exactly like taking the derivative. So we have f prime of t, which is the velocity, is 3t squared minus 24t plus 36. The next question is, what is the velocity after 3 seconds? So we take f prime of 3, which is equal to 3 times 9 minus 24 times 3 plus 36. The next question is, when is the particle at rest? Well, the particle is going to be at rest when the velocity is 0, meaning when it's not moving, and when the speed is 0. So we can say f prime of t equal to 0, which is equal to 3t squared minus 24t plus 36. So we want something. So first we can take out a t, so we get t times 3 squared minus 8t plus 12 is equal to 0, or in other words, this is equal to 0. And now we want something that multiplies to 8. It multiplies to 12 and adds to 8, which would be negative 2 and negative 6. So this is going to be t minus 2 and t minus 6 is equal to 0, right? So 2 minus 2 is 8, and 2 times 6 is 12. So we get that the particle is at rest at time t equal to 2, right, when either this is 0 or time t equal to 6. So it's either t equal to 2 or t equal to 6. The particle is at rest. The next problem is, when is the particle moving in the positive direction? So the particle is moving in the positive direction when the velocity is greater than 0, meaning when its speed in the positive direction, right? We have the equation for its position, but we want to know when it's moving in the positive direction, when is it moving to the negative direction. When it's moving to the positive direction, we know that the velocity of the particle is going to be greater than 0. It's moving with a positive speed, meaning it's moving in the positive direction. So we're going to have f prime of t. We want this to be greater than 0. So in other words, we want 3t squared minus 24t plus 36 to be greater than 0. So by the same calculations as before, we want t minus 2 or t minus 6 times t minus 6 to be greater than 0. So when is this the case? Well, if both of these are positive, then we're going to be greater than 0, right? And both of these are positive when t is greater than 2 and t is greater than 6, and t is greater than 6. So both of these will be positive, and so the whole thing will be greater than 0. Another time where this whole thing is positive is when t, for this condition, if we satisfy this, we satisfy this, so we can pretty much just get rid of this. And the first condition is we need 2 to be greater than 6. The second condition is that we need t to be less than 2, which means that over here we're going to have a negative, and t is less than 6, which means that over here we have a negative. But if t is less than 2, t is going to be less than 6, so we can ignore this. So we have that if t is either greater than 6 or t is less than 2, we have that, so if t is greater than 6, these are both positive, and we're good. If t is less than 2, then we're both negative. They're both negative, and again, the whole thing is going to be positive. If t is in the middle, so let's say we have t equals to 5, then over here we're going to have a positive number, and over here we're going to have a negative number, and we're going to have a negative number. So this is what this is when the velocity is greater than 0. Okay. Find the total distance traveled during the first 8 seconds. So we know, so we want to look at the first 8 seconds. So again, t is less than 6, and t is greater than 6, or t is 2. So we want to look at the first 8 seconds. So we know that from the 0th second until until t is 2, the particle is traveling in the positive direction. So we can use the equation for the position, which is again f of t is equal to t to the third minus 12t squared plus 36. We can use this equation to calculate where were we at time 0 and where were we at time 2 in our position. And because that we're traveling in the positive direction, we can just plug in the points directly. So we can just take f of 0 minus f of 2, and in order to calculate the distance, we'll just take the absolute value. Now we can't just go from f of 0 to minus f of 8, right, which is what we really want to calculate, where we were at 0, where we were at 8, because it's really possible that we, as time goes on, we move forward and then backwards and then forwards and backwards, and then if we calculate f of 0, we'll get some number, let's say 1, and we calculate f of a and we get 1, and so we'll say, oh, the total distance traveled is 0, right, because we're going to just get the absolute value of 1 minus 1, which is absurd. We went back and forth and back and forth, so we traveled, we just ended up on the same place. But if we know that, listen, we went a certain amount in the positive direction from a certain point to a certain point, from let's say 1 to 2, right? So we went from a certain point to a certain point, so we can calculate that distance, which is exactly what we're doing. Then we say, okay, now we're going backwards, but now I'll just calculate what this is, which is exactly taking the absolute value of this minus that, and then we'll get this distance. We'll add it to the first distance, and then we'll just keep on doing this. So we won't just go blindly and calculate the first distance, the first position that we want, and the last position that we want. We will remember when we're going forward, and until we start going back, so we'll just calculate all the times that we're moving forward, and just take the absolute value of that. All the times that we're moving backward, take the absolute value of that. We're going to add all of that up, and we're going to get our total distance. So this is when we're moving forward, and we calculate what this is, and this is going to be, so when we have f of 0, we're going to have 36, the absolute value of 36 minus, and for f of 2, we're going to have 8 minus 4 times 12. Let me just put in a calculator. And we have 4 times 12, which is 48. So you're going to have 48 here, plus 36, and this is going to give you this is going to give us -4. So we're just going to plug it in. So we're going to get a plus 4 over here. So in the beginning, we travel 40, and then plus, and now we're going to take the next time. So now between 2 and 6, we're traveling backwards, but we take the absolute value, so we're going to get some positive number. So we're going to take the absolute value of f of 2 minus f of 6. And we know that during this entire time we're traveling in the same direction, so finding the distance is just taking one minus the other. So f of 2, as we already pointed out, is negative 4. And then you're going to get minus f of 6, and let me just plug it into a calculator. So you're going to have 6 to the third power minus 12 times 6 squared. So you're going to get, so this gives you minus 180, or in other words, we get, what we get is 184. So this is going to be plus 184, and plus, and finally we're looking at the last part of this, which is between 6 and 8. So we're going to take the absolute value of f of 6 minus f of 8, and just plugging it in, so we know what f of 6 is. So we have the absolute value of negative 180 minus an f of 8. Let me just plug in an 8, and this is going to be plus 220. I believe that over here we should have taken away a 4 probably. Let's just do that. So this is going to give us 332, I believe. No, 42, something like that. So anyways, plus 42. Just make sure the arithmetic is correct, but in the end of the day, the main idea, again, is that we might be going forwards and then backwards and forwards and backwards, and we figured out exactly when these changes happened, right? So let's do it according to what we know, which is that from 0 until 2, we're going forwards, and then from 2 until 6, we are going backwards, and then from 6 until 8, we're going forwards again. So we're going forwards from 0 until 2, and then from 2 until 6, we're going backwards, and then from 6 until 8, we're going forwards again. All right, forwards, back. So basically what we want is we take the absolute value of f of 0 minus f of 2, which gives us this whole thing right over there. And then we add to it the absolute value. And now what we want is this, and we can find that using the absolute value of f of 2 minus f of 6. And again, the reason we can't just take the absolute value of this minus that is because that basically what we will be finding is this distance, which is not what we want. We want to find this distance plus that distance. And then we take the absolute value from here to here, which is f of 6 minus f of 8. Okay. I'm not going to draw the diagram, but let's find the acceleration at time t and after 3 seconds. So again, we have f of t is equal to t to the third minus 12 t squared plus 36t. So f prime of t is going to be 3t squared minus 24t plus 36. And so then f double prime of t is going to be 6t minus 24. And this is the acceleration, and then after 3 seconds we're going to get f double prime of t of 3 is going to give us 18 minus 24. Okay. 18 minus 24 which is -6. Oh, now I just figured out that there's a t here. I made a mistake because I don't have a t here, so all of this is wrong. But again, the main idea is, we're going to do the same thing, which is talked about over here. Just plug this in. Plug in this, plus this, plus this, and you'll get the right answer. But just make sure to plug it into the right direction. I just didn't have a t when I was plugging it in. Okay. So now we are asked, when is the particle speeding up? When is it slowing down? So I don't know. I'm talking about speeding up. I'm not sure if that's like the best thing, but we can talk about when is the velocity greater than 0, when is it less, and when is the acceleration greater than 0, and when is the acceleration less than 0. So we have, for the velocity, we have that between for t greater than 0 and less than 2, or t greater than 6, we have the velocity is positive. For the acceleration, we have, so we want 6t minus 24 to be greater than 0, another 6t to be greater than 24, or t to be greater than 4. So we have that when t is greater than 4, the acceleration is positive. In all other cases, we're going to have that the velocity is negative or the acceleration is negative. So we can think about it this way. If, let's create this little chart. If you have a positive velocity and a positive acceleration, then you're speeding up, because you're going this way and you're speeding up in this way. The acceleration is moving you faster in this direction, so you're speeding up. So let's just use u for up. If you have a if your velocity is negative and your acceleration is negative, so you're going this way but you're also speeding up in this direction, then again you're speeding up. Maybe you're going in the negative direction but you're speeding up. But if your velocity is positive and your acceleration is negative, meaning you're going in this direction, your speed is in this direction, but you're accelerating in this direction, so you're slowing down, meaning you're stopping to go as quickly in this direction. You used to go in this direction, a certain speed. Now your acceleration is negative, so you're accelerating in this direction. You're being prevented from going quickly in this direction, so now you're slowing down. So let's use d. And similarly, if this is negative and this is positive, then you are slowing down. So if t is between 0 and 2, what's happening is that your velocity is positive, but your acceleration is negative, because your acceleration is only positive when t is greater than 4. So if you're between 0 and 2, your velocity is positive, your acceleration is negative, so you're speeding down. So you're slowing down. So you have slowing down. And then if you are between 2, then if you're between 2 and 4, so if you're between 2 and 4, then we have that your velocity is negative, right? Because t is only positive if it's greater than 0 and less than 2, or it's greater than 6. So if you're between 2 and 4, your velocity is negative, and your acceleration is also negative, because your acceleration is negative when you're less than 4. So you're speeding up. And then, right, finally, so now if you're between 4 and 6, if you're between 4 and 6, then your velocity is negative, but now suddenly your acceleration is positive, so you're again slowing down. 4 is less than t is less than 6, so you're slowing down. But if you're between 6 and 8, now your velocity is positive again, and your acceleration is positive. So you're speeding up. You. Okay. That's the end of that problem. So let's do the next problem. We have f of t. F of t is equal to 0.01 t to the fourth power minus 0.04 t to the third power. So that's that is your position. So again, we're asked find the velocity. So f prime of t is equal to 0.01 times 4t to the third minus 0.04 times 3t squared. And then find the velocity at after 3 seconds. So f prime of 3 is equal to 0.0143t minus 0.043 3 squared. And then we want to know when is the particle at rest. So again, we want the velocity to be equal to 0. So we're going to have 0.014t to the third minus 0.043t squared is equal to 2. We can take out a t, so it's at rest either. So let me just plot this. I mean, it can be done analytically. Oh, actually, I'm not going to even solve it. I mean, you can take out a t and say, well, at t equals 0, it's going to be a rest, and then you're going to have some equation with t squared and a t, and you can use the quadratic formula to find the other answers, and you'll get some solution. But I'm not going to do that. But again, the idea is that when this is equal to 0 for the t's, we're going to get that the particle is at rest. So let me just plot it actually so we can move on to the next question. So we have 0.01 4 times 4. I'll just pause it and write it out. So we have that this is at rest at 0 and 3. So for the next problem, when is the particle moving in the positive direction? So again, this is every time that this is greater than 0, and just looking at this, that's going to be if t is greater than 3. Otherwise, it's negative. So 3 is greater than t. This is moving in the positive direction. Find the total distance traveled the first 8 seconds. So we're basically going to go from f of 0 minus f of 3, which is when we're going in the negative direction, and add f of 3 minus f of 8, which is when we're going in the positive direction. Right? I'm not going to do this, but again, you just plug it in and you'll get. So now find the acceleration. So again, we have f of t is equal to 0.01 t to the fourth minus 0.04 t to the third. So f prime of t, which is the velocity, is 0.01 times 4 t to the third minus 0.04 times 3 t squared, and f double prime of t is going to be 0.01 times 4 times 3 t squared minus 0.04 times 3 times 2 times t. And so when after 3 seconds, we're going to have f double prime of 3 is going to equal to 0.01 times 4 times 3 times 3 squared minus 0.04 times 3 times 2 times 3. And then for the last one, when is the particle speeding up? When is it slowing down? So I'm going to calculate when is this equal to, I'm just going to graph it and see when is this positive and when is this negative, and then we can do it. But we know again that, so let's say we draw a table. we know that we have time and we have velocity, let's say, and acceleration. So for time so for time 0, the velocity is I believe 0, but let's call it positive, and then until this is true until time t, until time, oh sorry, negative. This is true until time 3. Let's just write it. Between 0 and 3, the velocity is negative, and then from 3 to 8, the velocity is positive. Now we just need to find the acceleration. So the acceleration is negative from 0 to 2, and it is positive from 2 to 8. So this is acceleration is negative, and this is going to be acceleration is positive. So let's just add some components to our table. So we're going to have velocity and acceleration. So we're going to have from 0 to 2, we're going to have negative velocity and negative acceleration. From 2 to 3, we're going to have negative velocity and positive acceleration, and then from 3 to 8, we're going to have positive for both. So over here, we're speeding up, slowing down, and speeding up again. So the next point to do is problem 7, which we've done similar problems a lot. The position function of the particle is given by s is equal to t to the third minus 4.5 t squared minus 7t for t greater or equal to 0. So when does the particle reach a velocity of 5 meters per second? So again, s prime is going to be 3t squared minus 4.5 times 2t minus 7, and we want to set this to equal to 5. In other words, we want 3t squared minus 4.5, so this is going to be minus 9t, and then minus 12 equal to 0. So we can take out a 3, so we're going to get t and then divide it with the 0, so t squared minus 3 minus 4 is equal to 0, or t minus 1 times t, so let's do t plus 1 times t minus 4, right? They multiply to 4, they add to 3. So this is equal to 0, so t equals to negative 1, or t is equal to 4, but we don't have, it's only for t greater or equal to 0, so this doesn't count. So at t equals 4, we reach a velocity of 5. So now we want to find the acceleration at 0. So let's just erase this, so we can just take the second derivative of s. So the acceleration is going to give us s double prime is equal to 6t minus 9. And then at 0, we're just going to get minus 9. Sorry, it asks when is the acceleration 0. So this is going to, we're going to make this equal to 0. So we're going to get 6t is equal to 9, or t is equal to 9 over 6. So before this value, the acceleration was either positive or negative, and then the acceleration stopped being that, turned to 0, and is probably going to change. And that's, I guess, what the value is. Okay, so problem 8, next couple of problems are the same. Let's actually look problem 11. So a company makes computer chips from square wafers of silicon. It wants to keep the side length of the wafer very close to 15 millimeters, and it wants to know how the area a of x of the wafer changes when the side length x changes. So we're going to have this little thing. We're going to have side x, an x, and its x is really close to 15 millimeters, and we want to know a of x. So a of x is going to be equal to x squared. Um, so we want to find the derivative and explain its meaning in this situation. So a prime of x is going to equal to 2x. Plugging in for 15, we get a prime of x is equal to 30. So, and this is millimeters squared because we have that side and that side. So what's going on is when x is 15, as we increase the x from 15 to something close to 15, a little bit bigger, the area is going to increase by 30 millimeters squared, or at least it's increasing at that rate. And now show that the rate of change of the area of the square with respect to its side length is half its perimeter. Try to explain geometrically why this is true by drawing a square whose side length is x, is increasing by amount x delta. How can you approximate the resulting change in area? So first we want to show that the rate of change with respect to the side is half its perimeter. So the perimeter is going to be 4x. The rate of change is 2x, so it's going to be half, right? So we're going to have 2x over 4x is equal to a half. So with respect to its perimeter, its range of change is half. So is this true? So if we create our little box, this is x, and then we increase it a little to something like this, where this is delta x. So we're increasing it by delta x. So what is the area now? So we can look at the area. We can look at the area that we're increasing by. So the change in the area is going to be this plus this plus that. So this is x delta x, and this is the same thing. So we get two of those plus, and this is just delta x times delta x. So it's delta x squared. So the change in the area, the change in the area is going to be 2x delta x plus delta x squared. And so the change in the area over the change in x and how much we added is going to be this over the change in x, which is equal, so we can take out a change in x, which is equal to 2x plus delta x, right? Because this is going to cancel with that in one of those, which as delta x goes to 0, so anyways, so this is the rate of change, and as delta x goes to 0, we get 2x, which is what we found. This is exactly what would happen if you just take the definition of the derivative and you make delta x being h. And so the next question is kind of similar. It says sodium chloride crystals are easy to grow in the shape of cubes. So you're going to have a cube in 3 dimensions, whatever. And we're growing crystals on this by allowing a solution of water and sodium chloride to evaporate slowly. If V is the volume of such a cube with side length x, so we have V is equal to x cubed. So we want to calculate the change in the volume over the change in x when x is equal to 3. Well, so this dV over dx is going to be 3x squared, and when we have 3, we're going to have 3 times 3 squared, or in other words, what we're going to have is 9 times 3, 27. And so then the next question is, what is the meaning of this? And the meaning is pretty simple. It's that when the cube has length 3, changing it slightly will change the volume of the cube, meaning the volume of the cube, its rate of change with respect to how much x is changing when x is equal to 3 is 27. So the next part is show the rate of change of the volume of the cube with respect to its edge length is equal to half the surface area of the cube. So we just have to figure out what the surface area of the cube is, and the surface area of the cube is going to be 6x squared. So so that area, so we have this, so this is a half of that. And I'm not going to do the geometrical argument for this, but it's the same thing. So the next question, interesting. Find the average rate of change of the area of the circle with respect to its radius r as r changes. So we have a circle, and we have the radius r, and we want to find the rate of the change of the area of the circle with respect to r. So we know that the area of the circle is equal to pi r squared. So the change in the area over the change in r is going to be 2 pi r, which is very interesting. So the question actually asks us, find the rate of change of the area of the circle with respect to the radius as the radius changes. So for one of them, let's just look at one of them. We have the radius changing from 2 to 3, and for the second one, we have the radius changing from 2 to 2.5, and the third one we have it changing from 2 to 2.1. And the way you would basically do this is you would say, okay, so you're going to have the area, you're going to have the change in area, which will be the area at 2 minus the area at 3. So you're going to have the area 2, which will be pi r cubed, 3 squared, minus pi 2 squared over the change over here, which is 3 minus 2, and so on. And you're going to do this for each one. And I assume as you get closer and closer to 2, as this gets closer and closer to 2, you're going to get closer and closer to 4 pi. Because if you plug in a 2, the instantaneous rate of change when we have r changing from 2 to something slightly bigger than 2, the rate of change is going to be 4 pi. So I assume that this is getting closer and closer to 4 pi. I'm not going to actually do it. Okay, so that will be that's for the question. But interesting thing is that the rate of change is 2 pi r, and so you plug in the r, and you will, for any r, we'll know the rate of change of the. So the next problem, so we have a stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. So you have your lake, a stone is dropped in, and it creates this wave that travels outwards at a rate of 60 millimeters per second. Find the rate at which the area within the circle is increasing after 1 second, 3 seconds, and 5 seconds. What can you conclude? So what we want to be able to do is to get a function such that if we plug in a time, we'll get the rate of the change of the area of the circle over that time. So what we want, just to think about it, is the change in the area over the change in time. Right? We want to know how the area is changing as the time goes by, because we want to plug in time is 1 second, time is 3 seconds, and so on. So we know that the area is equal to pi r squared, and so we definitely can find the change in the area over the change in the radius, which is 2 pi r squared. But how can we turn this into time? How can we make this so that we have this? We don't really want the change in the area over the change in radius. We want the change in the area over the change in time. Well, we can use the chain rule for that, because we know that r can be written in terms of time, right? Because r is equal to 60 times time, right? For time, right, we're changing at a rate at 60 centimeters per second. So for the first second we have 60, second second, the radius of this ripple is going to be 120, and so on, right? For every second, the radius of this ripple is increasing by 60 seconds. So we can write the change in the area over the change in time. Well, that, by the chain rule, is going to give us the change in the area over the change in r times the change in r over the change in time. And this we know, right? Because we wrote, that's easy. The change in area over the change in r is just going to be 2 pi r. So this is easy. So we already have the first part. This is going to be 2 pi r. Well, what is this? What's the change in the radius over the change in time. Well, just look at this. Well, if we take the change in r over the change in time, what we just get is 60. It's just a constant. This is 60 times time times the second. Well, we get a constant. So this over here is just 60. So we write 60 over here. But now we want this completely in terms of time. So we can take this r and just put in times over here, and we're going to get 2 pi, and then we plug in the r, so we're going to get 60t times 60. Or in other words, we're going to get 2 pi t 60 squared. So we have, and again, we just have to keep track of what we know and just write things out. So we have that the change in the area over the change in time is just equal to 2 pi t 60 squared. And now we can just plug in our values. For let's just do for the first second. So for t equals 1, we get that this is going to be 2 pi 60 squared. That's the change. So as the time is changing, the rate of change is going to be that. Okay, next problem. So this is problem 15, and we have that a spherical balloon is being inflated. So, you have a spherical balloon. That is definitely not how it looks, but whatever. And it is being inflated. Find the rate of increase of surface area. So they give us the surface area is going to be equal to 4 pi r squared with respect to the radius r, when r is whatever. So all we have to do, given that we're looking for it with respect to r, and r is right in our equation, all we just do is take s prime, which is equal to 8 pi r, and we're done. Okay, next problem. And then we just plug in the r's that they give us, and that's that. So the next problem, the volume of a growing spherical cell is V equals 4/3 pi r cubed, where the radius is measured in micrometers. So find the average rate of change of V with respect to r when r changes. So again, it's just going to be V prime is equal, the 3 drops out, we get 4 pi r squared. And this is the instantaneous rate of change. They also want us to find the rate of change when r is 5, going between 5 and 8. R is changing from 5 to 8. And that would just be to plug in this for 8, let's say. So we're going to have, right, we can look at this as f of x and this as x. So we're going to have just, 4/3 pi times 8 minus 4/3 pi times 5/8 minus 5, and so on. And they're getting closer and closer. So the last one they ask is 5 from 5.1. And they basically want us to find the rate of change. And then they ask us to find it with respect to 5. So that instantaneous, so that would just be this is equal to 4 pi 5 squared. And these should be very close. That's the idea. And then they say, show that the rate of change of the volume of a sphere with respect to its radius is equal to its surface area. Well, so this is the change in volume, and this area was given over here, 4 pi r squared. See that they're the same. V prime, the volume over here, is equal to the surface area. A very interesting fact. And I'm not going to explain geometrically why it's true, but again, you're going to use doesn't create a whole thing about it. Okay, so next question, the mass of the part of the metal rod that lies between its left end and a point x meters to the right. So we have a rod, and we have, let's make it more like a rod, and we have that the mass between its left end, and so here's our left end, and a point x meters, so any point, whatever it might be, x meters, is going to be 3x squared. So for any x, you're going to basically plug it into here, and you're going to get the mass. So if you want to know the mass of all of this, we just plug in this x into here, and we're going to get the mass, and so on. So let's just write this more carefully, 3x squared. Okay. Find the linear density when x is 1 meter, 2, and 3, where is the density the highest and the lowest? So the linear density is basically how quickly is the mass changing of the rod changing at any given point, right? Clearly this thing is not like, it doesn't have equal mass, right? As you get higher and higher, this is kind of increasing. So to find the linear density, you just take the derivative, which is equal to 6x. And we want to know, when is 6x the highest? Well, 6x is always increasing, so it is going to be the highest for, they give us values 1, 2, and 3. It's going to be the highest for 3 and the lowest for 1, right? If this were not always increasing, we might have something interesting. But if it's always increasing, then the more you move up here, the bigger the linear density, or the more the mass is changing over the change in x. Like a little change in x will make the mass much, much bigger. Okay, so next problem, problem 18. If a tank holds 5,000 gallons of water, which drain from the bottom of the tank in 40 minutes. So let's say whatever, we have some tank and it has water in it, and it's 5,000 gallons, and it's draining from the bottom at a rate, and it's going 40 minutes later. Then someone, I don't know how to pronounce this guy's names, gives us the volume of the water remaining in the time after t minutes, as the volume is equal to 50,000, 1 minus t over 40 squared, right? So, and this is, t is between 0 and 40. Let's just kind of make sure this makes sense. Well, at time 0, this thing is 0, and then we just have 1 squared times 5,000, which is 5,000. So when we just begin, it's 5,000. And at time 40, this becomes 1, so we have 1 minus 1. This whole thing becomes 0, and then volume is 0. So that makes sense. So find the rate at which the water is draining from the tank after 5 minutes, 10 minutes, 20 minutes, whatever. So let's just take the derivative of this, which is going to be equal to 2 times 50,000. We're going to have a chain rule here, yeah? So 1 minus t over 40, and then times the derivative of this, which is going to be negative, and then we're at negative 40 times t gives us 1, and then minus t times 40 is 0 over 40 squared. So this is what we get. Actually, this is a mistake. We're not using, I was using the quotient rule, but we're not, because this is just equal to 1 minus 1 over 40t, and so this just is 0, and this is like a constant over t, so we get 1 minus 40. So yeah, so over here we're going to get, and even if we did it with the quotient rule, we would get the same result, which is negative 1 over 40, because even if we do it with the quotient rule, it's going to be 40, it's going to be negative, and then 40 times the derivative of t, which is 1, times 0 over 40 squared, and these are going to vanish. So I did not even do the quotient rule correctly, but whatever. So this is what we get, and then we just plug in values, and we'll know how the volume of the tank is changing over time. I'm not going to plug in the values, but that is the main idea. So let next problem. So the next problem I'm going to skip, problem 19, problem 20, actually, let's just do something with gravitation. So we have Newton's law of gravitation says that the magnitude F of the force exerted by a body of mass m and a body of mass big M is F is equal to G little m big M over R squared. This is big M and little m and so on. G is the gravitational constant, R is the radius, R is the distance between the two bodies. So first we want to find the change in the force over the change in R. So we want to know what this is, and this is basically going to be, so now we do use the quotient rule. We're going to get r squared times 0, and then we're going to get times negative g m 2r over r to the fourth power, or negative g little m big M. One of these should be little. 2 over r cubed. So the change in the force is basically getting smaller as r gets bigger and bigger, right? This shrinks, and regardless, it's always going to be negative. And that's because when two bodies get farther and farther away, we're always going to get a smaller force. So the force is getting smaller. So we have negative. And then they just give us examples to plug in, which I'm not going to do right now. So the next problem 21. Boole's law states that when a sample of gas is compressed at a constant temperature, the product of pressure and the volume remains constant. So we have the pressure and the volume is constant. Find the rate of change of the volume with respect to pressure. So we want to find, so volume is the same as C over P. So the change in volume over the change in pressure is going to be P times, so it's going to be negative C over P squared. So that's the change of the volume with respect to pressure. So then they ask a few other questions. So the next question, a sample of gas is in a container at low pressure and is steadily compressed at a constant temperature for 10 minutes. Is the volume decreasing more rapidly at the beginning or at the end of the 10 minutes? So is the volume, and the answer is that when P is very, very big, this becomes small, and so at the beginning, when there isn't a lot of pressure, the change in the volume over the change in pressure is very big. But later on, the more pressure you exert, the less the volume is changing, which makes sense. In the beginning, you have this thing, and you have a bunch of particles, and you change the pressure a little, and you shrink a lot. But in the end, everything is so compressed, you change the volume, you change the pressure, you have to exert a ton of pressure to change the volume even a little bit. And I am not going to do part C. So now, example 22. For example 22, you basically take the derivative again in terms of C. I'm not going to do that. I'm not going to do problem 23 or problem 24 or problem 25. And again, problem 26, you take the derivatives. Okay, so let me actually problem 22 and 26 because they look interesting. So if in example 4, one molecule of product is formed from one molecule less than 8 of the molecule. So basically, we're given a certain scenario, and it says that if it happens, we're going to have. We're taking two molecules, and we're trying to create a third, and the two molecules are A and B, and the third one is C, and C is given. The amount that we get for it is given by a squared over kt over a kt plus 1. So we want where k is constant and a is the moles of A and B. So we want to find the rate of the reaction at time t between the two molecules A and B, because we have A reacting with molecule B to create a third a product molecule C, and the moles for the initial constraints of A and B, we have the common value of A and B has the same amount of moles, which is A moles over, L. So anyways, so this is going to be taking the change in this over the change in time, which is just going to give us AK plus 1. Wait, is there a T in the bottom? Oh yeah, this is T. Okay, so let's rewrite this. AKT plus 1 times the derivative up here, which is just A squared K, minus A squared KT times the derivative down here, which is just A K all over AK plus 1 squared. So that's the rate of change. And then it says show that if x equals c, then the rate of change of x over time is just going to be equal to k a minus k squared. Sorry, this would be an x, a minus x squared. So this would just be geometrically to show that this and this are the same thing, which I'm not going to do, but I are. So now let's do problem 26. The frequency of vibrations of a vibrating violin string is given by, so this is the frequency, it's given by 1 over 2L times T times T over P. Where L is the length of the, well, it's not really P, but whatever. Where L is the length of the string, T is the tension, and P is its linear density, which we already spoke about. So find the rate of change of the frequency with respect to the length. So we want T and P to be constant, the tension and the linear density, and then we want to find the rate of change of this frequency. So we want to find dff over dl. Well, so this is a constant, and so this is just going to be square root of t over p times negative 2 over L squared, right? Just do the quotient rule down here. Sorry, and there should also be a 2 squared over here because this whole thing is squared. So this is basically going to be equal to negative 1 over 2L squared times T over P. So that's the answer for that. And then we want, second thing is the tension when L and P are constant. So we want to find the change in the frequency as we change the tension if everything else remains constant. So we're going to get 1 over 2L and then a half T over P to the negative a half times 1 over P, right? Because the chain rule over here, that drops down. So this is going to equal, let's just erase this and simplify it. So we're going to get 1 over 4L, and then we're going to get T over P, taking the square root of that, times P. So this is equal to 1 over 4L square root of T over the square root of P times P, which is equal to 1 over 4L square root of T square root of P, which is equal to 1 over 4L square root of TP. So now the last question, let's rewrite, just erase this. So for our last question, we have the linear density. So we want to find the change in the frequency over the change in the linear density, and then L and T are being held constant. So we're going to have change in the frequency over the change density is going to be 1 over 2L, and then you're going to have a half T over P to the negative a half. Then you're going to have the derivative of this, which is going to be P times the derivative of T, which is 0, and then T minus T times the derivative of P, which is 1 over P squared. So I can't do part B because that I no longer have the derivatives. I erased them, but it shouldn't be very difficult. Just look at the equations. I'm going to skip question 27. So let's look on 29, which says if P is the total value of production when there are X workers, so X of P is the total, when there are X workers in a plant, then the average productivity workforce at the plant is, so the average productivity is this. It's the total work productivity divided by the amount of people there. So let's find A prime of X. That's the first question, which is the change of the average productivity given when, like, as we add workers. So this is going to be X times the derivative of P minus Px over X squared. So now the question is, why does the company want to hire more workers if the average productivity is greater than 0? And the answer is because this would mean that the change in the average productivity over the change in workers is going to increase. So each worker is going to be worth more than the workers are currently worth, or the productivity of each worker is going to increase on average just by adding a couple of workers. So that's why basically you're going to get more work out of each worker. So per worker you're going to get more work. And now show that the average productivity is that if, so this, we want to show that if that the average productivity is greater than 0 if the change in productivity, so the change in productivity over the change in X, the change of workers, is greater than 0. Sorry, if this is greater than the average productivity. That is greater than the average productivity. So let's assume that it is. So we're going to have, let's see, we're going to have that the average, so we're going to have X, so let's see, so if we have P over X is greater than P of X over X, which is exactly what this statement is saying, then we are going to have that X times P of X is greater than P of X. So this is greater, this is positive, so this whole thing is positive, right, because X squared is positive, so X prime of X, and regardless X is positive, because we're going to have a positive workers, so X prime of X is also going to be greater than 0. Okay, so that was problem 29. So I think we're going to stop here, and the next one we're going to do is related rates. And maybe I'm actually going to spend 2 videos on related rates because everyone seems to have problems with it. So it just, going through every single problem carefully might take some time, but we'll see. We'll see how that goes.